When you record the mass spectrum of any compound, there's a ton of information that you can gain. Now you'd think that we'd start by talking about the masses, but we're going to talk about something different. And that refers to the isotope patterns. So for example, any spectrum that you see like here, it's not just the mass that we're recording, but we're getting all these patterns that give us more information about what the compound is. You might even be able to figure out what the molecule is just by looking at the ratios of those peaks. So we're talking about isotopes today. So just to make sure everybody's on the same page here, let's start with the periodic table, and why don't we begin with my favorite element, carbon. So what defines carbon atoms? Well, we know the answer. It's the number of protons. In this case here, we happen to have 6 neutrons, so the mass number is 12, and we call this thing here carbon 12. So let's just double that carbon atom over here, and what I'm going to do is throw in just a single neutron. Is that still carbon? Well, yes, it still has the same number of protons, so it's still carbon, except in this case it just happens to be carbon 13. You could say that basically these two atoms are identical in every single way, except one of them is a little bit heavier than the other. Not unlike me and my brother here. So what is the mass of carbon 12? Well, let's do it on the scale of kilograms, which I know doesn't really make sense, but just to get a sense of how small these things really are, we know exactly, or almost exactly, the mass of a proton, a neutron, and yeah, the electrons are a lot smaller, but let's add them in here. So if it's just a matter of adding them together, you can come up with this number. It doesn't mean very much. So if we convert these numbers to atomic mass units, you can see that, well, protons and neutrons, they're about 1, and the electron is just a fraction of that. We can add them all up together, and we end up with this number right here. Just a second. Something doesn't feel right. And it all boils down to this fellow right here, Einstein and his famous equation equals mc squared. The amount of energy that it takes to hold a nucleus together is actually extremely high relative to the mass of these compounds. So all that positive charge that the protons have, they're fighting against each other. That nucleus basically wants to explode. So it takes a lot of energy to hold that thing together. And that energy is actually taking away from the mass of our compound. So carbon 12, by definition, has a mass of exactly 12. And therefore, if you look at carbon 13, it is not the mass of carbon 12 plus 1 neutron. It's a little bit less than that. Now I want to put the issue of mass aside just for a second because I want to focus on isotopes in this particular video. Now we can look across the periodic table and we notice that some elements exist with only a single isotope. So for example, these fellows over here. Now still others exist with 2 isotopes, and by the way, with this I'm referring to the stable isotopes. So I know carbon 14 is radioactive, but we're not talking about the radioactive nuclei. And still you can look at elements that happen to have 2 different isotopes. Again here, wait a minute, oxygen 17 does exist and it's a stable isotope, but this is being classified as an A+2, in other words, it has 2 different isotopes, simply because the probability of 17 is really low compared to 18, so we're just kind of approximating and we're throwing oxygen into this category. Chlorine definitely only has 2 isotopes. Now most of the periodic table actually falls into this category here where they have like multiple isotopes. We're usually not going to be thinking about them, at least for the calculations that we're dealing with in this class. Now I know you're used to staring at the periodic table. You've probably even memorized the masses of several compounds to like several decimal places. You're going to have to forget those numbers, especially in this class here. So this table that you're looking at, I have it in my hand. And the last category refers to, well, the relative atomic masses, which you would get from the periodic table. When it comes to mass spectrometry, those numbers don't exist. So this is what you need to do. You got to get rid of those numbers, throw them away. And yeah, I'm going to be confusing you when it comes to the test. I will give you this table. Well, you have the table, right? I don't even need to give it to you. But this is the table that you need to be working with. Throw away the concept of relative atomic weights. So let's just peek at this atom over here. Now chlorine, as I said, exists with 2 isotopes, chlorine 35 and chlorine 37. And the isotopic abundance that you see is listed where just the most abundant one happens to be 100. So it's kind of normalized to the highest abundant sample. The lower abundant one, chlorine 37, is about 1/3 of the abundance. Now, if we wanted to express that like as a percentage where the 2 of them add up to 100, you could do these equations here and we could convert from one number to the other. So you see basically we're converting 100 divided by the total abundance, 100 plus 32 times 100%. So you can express those numbers either as a percentage or as a probability or a fraction. Now let's take a peek at what this looks like when we record a mass spectrum for chlorine. So just to make it easy on us here, let's actually focus on HCl. And you can see from the spectrum that you get this 3-to-1 ratio where the most abundant one refers to the HCl with chlorine 35, and then there's a 1/3 probability for having HCl 37. There's a 2 mass gap between them because 35, 37, there's a spacing of 2. And of course the mass happens to be 1 higher than chlorine because that's the mass of hydrogen. Couldn't be easier, right? Perfect. So let's get to something that's quite a bit more complicated. Carbon tetrachloride. Now let's just think about all the different combinations that we can have for this particular molecule. Well, we could start with carbon tet where chlorine 35 is the only atom that appears. But there's another chance of having chlorine 37 show up instead of 35. Let's just put one of them in there. Of course, it doesn't matter where chlorine 37 shows up because you could just rotate that molecule and it would be the same. What about 2? We could have 2 chlorine 37s along with 2 chlorine 35s, and you can extend to 3 and 4. We haven't even talked about carbon 13, but the same thing can kind of be copy-pasted all along. So this starts to become a mess very quickly. Like there's all kinds of different ways of combining these atoms together to create a rather complicated mass spectrum. But that's exactly what we're trying to do here. We're trying to calculate or predict a theoretical mass spectrum based on the abundance of all these atoms. Okay, I'm going to park that example aside just for a second. We're going to focus on something a little bit easier. So this is octane, which just has carbon and hydrogen in it. And we have our table here with the exact masses for deuterium, carbon 13. That doesn't matter in this right now. But the other thing that's not going to matter right now is the deuterium, just because the probability is so low. So I'm only focusing on carbon 12 or carbon 13. So we could write an equation for our compound that would look like this. Basically, it's all carbon 12. There's no carbon 13. And therefore, we can put another single carbon 13 in there, or 2, or 3, or 4, just writing formulas all the way down the line. If I wanted to calculate the mass of these compounds, I'll just kind of take an estimated number, say carbon 12 is 12, carbon 13 is 13, hydrogen, of course, is 1, and you just add them up. So you can do these simple equation calculations, and you can calculate the mass. Now, the odds of that molecule containing all carbon 13 are almost astronomically high. There's going to be a probability. In other words, in the lotto, somebody tends to win, but it's going to be a very low number. So if our goal is to calculate a theoretical spectrum, then we do need to know a little bit about probability, a little bit about statistics. So we're going to use the example of rolling some dice here, and you're going to see equations that look like this. Well, I won't really go into this one in too much detail, but let's just start with the basics. Let's just roll a single die, and you happen to turn up a 4. Now, what are the odds of getting a 4? Well, there's 6 faces, so the odds of rolling a 4 with one dice in one roll is 1 on 6. What are the odds of rolling 2 4? Well, each of these dice has a 1 in 6 chance of getting that 4, so you multiply the 2 together. There's a 1 in 36 chance of getting 2 4s. And we can extend this logic further. If you happen to have n dice, then the probability of each of them is 1/6 raised to the power of n. So that means that if you're trying to roll in one single roll all 6 die to get the exact same number, the odds are going to be kind of astronomically high. In this case, it happens to be 1 in 7,776 to land that roll right there. So just one more thing I wanted to add here. Now, what are the odds of rolling like, I don't know, a 6 and then not rolling a 6? Well, all you have to do is add up all the different ways that you can not roll a 6. And there happens to be 5 different ways. So we can just know that our probability of the first one is 1 on 6. The probability of not getting that first one is 5 on 6. And then you just multiply the 2 together. Almost, because there's another combination. Because you don't have to roll that 6 on the first roll. You could roll it on the second one. So there's actually 2 different combinations of doing that. You'd have to take this equation and multiply it by 2. We'll get to this again when we start talking about the probabilities of our molecules. Okay, we're back to our list here. We're looking at octane, and we're going to start first by focusing on just having carbon 12. So what are the odds of having octane where every single atom is carbon 12? So you imagine it like a bunch of boxes, and yeah, I'm completely ignoring the contribution from hydrogen. So what we need to do is put 8 carbon 12s, one into each of those boxes. So it's just like rolling a dice. We just need probabilities here. What is the probability of a carbon 12? This comes from our table. And notice that I'm using the probability as a percentage. So we're focusing on carbon 12, this is 0.989. There happens to be 8 carbons in here, so we're going to raise that to the power of 8. So we just do this calculation, and it turns out that the odds of finding carbon-12 exclusively in octane is about 92%, or a 0.918% probability. So most of the time it's carbon-12. Now what about having one carbon-13? So what I'm going to do here is I'm going to place a single carbon-13 into my boxes, and the rest will have to be carbon-12. And keep in mind that it really doesn't matter where the carbon-13 shows up, because the mass of that compound is going to be the same. You can actually arrange this into one of 8 different spots. So whatever the probability is, we're going to have to multiply that number by 8, because there's 8 different combinations that we can come up with. So from the table, we actually have to pull on both numbers, the probability of carbon-12 and the probability of carbon-13. We're only using one single carbon-13, so that number is raised to the power of 1, and we have 7 carbon-12s. The probability of carbon-12 is 0.989. We raise that to the power 7. The 8 that you have in the front there, that's because we have 8 different places that you could put the carbon-13. So when you do this calculation, the probability is about 0.079, or roughly 8%. So carbon-13 can show up more likely because our molecule has 8 different chances to throw it in there. The larger our molecule is going to get, or in other words, the more carbon we have in our molecule, the more abundant or the more probability we have in actually finding that carbon-13 showing up. So let's just express that equation as a general formula. N is the number of carbons, and P is the probability of finding carbon-13, so 0.011. Now, the other thing that's relevant for us to calculate here is actually the ratio. In other words, the ratio of finding one carbon-13 over the ratio of not finding carbon-13. What we're doing is we're expressing the ratio of the first 2 isotopes in our mass spectrum. So we happen to have the equations for each of these expressions, so all we need to do is divide one by the other. You can take this expression and simplify it just a little bit, and if you wanted to express it as a percentage, you just multiply it by 100%. So you can see from this equation that the probability depends only on the number of carbons and the abundance of carbon-13. Now I'm going to spare you the calculation of going through the probability of finding 2 carbon-13s, realizing that there's a lot of different combinations that we can get, but it still boils down to the expressions that I showed you before. So just skipping ahead to the final formula, the ratio of the abundance of the 2 carbon-13 over no carbon-13 is this equation right here. So you can come up with similar expressions for essentially all the atoms. And what I'm doing here is I'm inputting the real value for the probabilities. So you're not actually seeing the equation in these expressions, you're just taking the numbers and throwing them in. So when you're looking at the A+1 isotope, in other words, the isotope that's like one mass shifted up from the monoisotopic peak, what you'll see is that it depends on the number of the different atoms that we have. And you can come up with another expression for the A+2. And notice here that chlorine and bromine are dominating, even though they're not in the A+1, simply because we don't have these isotopes that are separated one mass unit from the other. So these are quite important equations. They're useful for you to do kind of a quick calculation to figure out the intensity of the A+1 and of the A+2 isotope. So we can use those expressions to calculate at least a couple from the series over here. In fact, this equation right here would be used to calculate that one, right? And then the next one on the series, A+2, so in other words, 2 mass units higher than the base, would be using this expression right here. But what about all the rest? Well, actually it gets pretty complicated. So let's just simplify this one step by ignoring the carbon-13, because carbon-13 is only at a 1% probability, where our chlorine-37 is like 32% probability. So we've just basically done the same as I did for my octane example, where we ignored the hydrogen. So just like our dice problem, we do need to think about the different permutations, the ways that we can arrange these series. Now the first one and the last one of the set are obviously the easiest ones. There's only one way that we can get all chlorine-35 or all chlorine-37. Likewise, it isn't that complicated to think that the chlorine-37 can only show up in one of 4 places, so there's 4 different ways that we can get this particular molecule. Same thing over here, where we're just thinking about the chlorine-35. Now the one in the middle is where we're going to have to dig out this equation here. If you're not familiar with it, it's pretty straightforward. We're talking about permutations, so we're thinking about the size of the set and how many samples we're going to pull from the set. So the set size is 4. We have 4 different chlorines, and we're going to take 2 chlorine 37s out of it. So the calculation we're going to do is just to rearrange those numbers, 4 factorial, 4 times 3 times 2 times 1, over 4 minus 2 factorial, and that works out to 6. So there's 6 different ways that you can arrange to have chlorine 37 showing up twice. And now we can calculate our probability. So we know the probability of having chlorine 35, we know the probability of having chlorine 37 in the table. So we just have to think of this the same as our dice problem, and how many times each of these things will appear. We raise that to the exponent. Once we have those, we multiply by our combinations, number of permutations, and we get the total probability. Now, fortunately, there is an easier way to think about this. So this is a different equation that can be used for this particular situation of calculating the isotopic distribution. And here we're only concerned about one atom at a time. So we're only looking at the chlorine, for example. So chlorine exists with 2 different isotopes, and there's their probabilities for each of them. But instead of chlorine, we could have any atom. So you can think of this as just a probability A and B. So for the molecule carbon tetrachloride, we're going to write down this expression here. A plus B raised to the power of N. N refers to how many times we're using that chlorine in the molecule, or any atom within that molecule. So here, N equals 4 chlorines. So the next thing we do is we're going to expand that expression. So you can write this kind of nasty equation here, but it has a rhythm to it. So it's a to the power 4 in the first term, a to the 3, a to the 2, a to the 1, and a to the 0. And you can work your way backwards, b4, b3, b2, and b1. But we're not quite done. Now what about the coefficients in front of these terms? So basically we can use Pascal's triangle here, and just to remind you, the number in the next row down refers to adding the 2 numbers above it. So for n equals 4, you're using this row here, so those are the coefficients that would show up in that particular equation. Well, let me just write this down here and clear the board. So we have all of these different expressions, and each one of them actually refers to the abundance of one of the isotopes. We have our values for A and B for chlorine, but it doesn't have to be chlorine. You could put any atom in here. And all we're going to do is expand this expression and calculate the numbers. And yeah, in this case, they show up to be pretty big numbers. Of course, if you use the probabilities 0.76 and 0.24, you're going to get small numbers. Here I just put in 76% and 24%. It doesn't matter how they work out, because ultimately what we're going to do is we're going to normalize these numbers. So you see the biggest number that we have is the 42 million. We're just going to call that 100%, and everything else gets normalized to that number. Now here's the beauty of it. Those numbers that we've just calculated actually work out to be the probability for each of these different arrangements. So if we're plotting a mass spectrum, then we're going to use those isotopic abundances as our intensity for each of the ions. And there they are. So you see the numbers from the previous page. We have about 80 to 100 to 50 to 10. Now I didn't write the masses just yet, but that's pretty easy to calculate. So if you think of carbon 12 and chlorine 35, of which there's 4 of them, you just bring those numbers together and you end up with 152. The gaps between each of these isotopes is 2 because of the mass of chlorine 37. So you're looking at the first one that has 1 chlorine 37, or 2, or 3, or 4, but where did that one go? Well, it's there, but it's like the probability is so low, so it just doesn't even show up on that scale. Likewise, carbon 13 is showing up. You can see it just as a small bump in between. So if I just kind of zoom in on that, the mass scale does show me the carbon 13. And the pattern almost mirrors itself. It just shows up with a lot smaller probability. We only have 1 carbon, so it's about 1% of the abundance of the pattern before it. Yes, I know that can get pretty complicated, so practice your problems, but there fortunately are a lot of websites out there that do all these calculations for you. My personal favorite one is this thing called ChemCalc, so I'll just take you to that right now. And what you can see is that basically you enter a molecular formula, so carbon tetrachloride that we just did, and instantly it tells you the pattern. You can even click this button right here, and it's going to download on a little Excel table. So you get the exact numbers for all of these things, and it even calculates you the exact masses, which we'll get into in another lecture. Let's just try another molecule here, C100, H200. Look at that. The X plus 1 isotope is even more abundant. Just chlorine, just bromine. The other feature I want to show you is that you don't have to plot this at sticks. So I can create width to each of these spectra. So I'll just add a number, I don't know, 0.1 or something. and you see that the peaks are getting wider. So if we go back to carbon tetrachloride, there's the pattern that we saw that looks more familiar. If I want to change the peak width, I can make them even wider here. And we get a spectrum that looks like this. Oh yeah, let me just show you one more thing. This is always assuming that the charge is +1, the m over z. What if the charge is 2? Well, you can change that as well. So if the ion's charge is, I don't know, +2, then you get this pattern here. It's actually half of what it was before. We'll talk about that in another video. So yeah, that's about it for now. We'll be checking out a lot of the other features that ChemCalc can provide us in later videos in this class.